Hello, and welcome to the lecture for Chapter 7 from OpenStax Astronomy, where we're going to talk about an introduction to the solar system. So that means we're going to introduce the solar system in broad terms. Okay? So as we as humans have explored the solar system, we've learned a lot about it. One of the planets, other than Earth, of course, that we've learned the most about is Mars, because we've sent so many missions there, such as the Curiosity rover shown in this picture. We have allowed these rovers to drive around in semi-autonomous states, taking tons of data through pictures and sampling of rocks and so on. We've never sent humans to Mars or any other planet, but we have sent these sophisticated rovers to the surface of Mars. We've also sent space probes, whether landers in the case of Venus or Mercury, or flyby missions that orbit planets in the case of Jupiter, Saturn, Uranus, and Neptune. All those planets, we have either flown past them or explored them in some sense. So every planet in the solar system has been visited by a space probe, either a sophisticated sophisticated rover, maybe just a lander in the case of Venus, and as I mentioned, all those flyby missions. Okay, so lots of exploration, and not just planets. We've gone to moons of the gas giants. We've gone to asteroids and comets. So really, a lot of impressive study and exploration has occurred in this vast solar system we call home. Now, the place that we've sent humans other than Earth has only been the moon. Okay? That's the only place that humans have walked other than the planet Earth. The moon is about 350,000 kilometers from Earth. It's much closer to Mars. It's a much faster mission to get there, although we are hoping to send people to Mars as well. That's our best target. It would not make sense to send people to Venus, for example, because the planet is so hot and the atmosphere is so incredibly dense, which makes for a huge pressure on the rocky surface of Venus. So humans would never survive there. We could potentially send humans to Mercury, but it's very high radiation due to its closeness to the sun and incredibly huge temperature fluctuations. So a place where a human could foreseeably survive with a good sophisticated spacesuit like those used on the moon, would be Mars. That's a place we could actually send humans. There are some moons of the Jovian planets, which are the gas giants, which could also potentially support astronauts landing on them. But they're even further, so we're talking about many-year missions to get there. A mission to Mars that would send humans there would take a few months. So it's still a very long flight there and back, but it's a actual possible mission in the near future. Now, here is an overview of the solar system. There's a lot of details in here. What's going on with the solar system? Well, first, let's take a look at the planets themselves. Now, the sun makes up about 99% of the matter in the universe. So when we talk about, the matter in the solar system. So when we talk about the solar system, everything we talk about that is in the sun is that last 0.1% of leftovers. Really, the solar system is the solar. It's the sun, and the sun formed as this compression of gas and a formation of as all stars form, and the leftovers, the remnants that didn't get gravitationally pulled into that star, our sun, are what formed all of the planets. Okay. Now there are rocky planets that exist near the sun. Those are in order from closest to the sun: Mercury, Venus, Earth, and Mars. Okay, those are the terrestrial planets. Terrestrial. Okay, these planets exist close to the sun because gases, hydrogen-based gases, evaporate at these locations closer to the sun. The space is warmed up from the radiative energy coming off of the sun, and so gassy planets cannot form in this region close to the sun. But as we go further out and we get to the orbit of Jupiter, we get to a point where the distance from the sun is sufficiently far that hydrogen-based gases, atomic hydrogen itself, but lots of other common gases like methane and ammonia, are able to form and not just readily evaporate. And those gases then can clump together and form huge planets known as the gas giants, which are in technical terms called the Jovian planets. Okay, so the Jovian planets are the gas planets, the terrestrial planets are the rocky planets. There are 4 rocky planets, as I already mentioned: Mercury, Venus, Earth, and Mars, in that order. Going with the Jovian gassy planets, or gaseous planets, starting closest to the sun and moving outwards, we have Jupiter, Saturn, then we have Uranus, and then finally at the greatest distance, Neptune. okay? Now, one thing about all these planets is all the planets basically form a plane of orbit, okay? So as we see in this 3D image, okay, all the blue lines represent the circular or slightly elliptical orbits of the planets. And honestly, some of the most distant planets, Neptune and Uranus, have fairly elliptical orbits. But you know what they all have in common? Is they all orbit in a plane. Okay, so there's very little shifting of their orbits. It's like a disk, like all the planets' orbits form a disk, a very sparsely populated disk, because there's mostly empty space between these planets. Again, there's just the leftovers from the solar system, of course, but they're all in that same disk. And that's explained by the physical process of conservation of energy and especially angular momentum that leads basically all solar systems to seemingly have their major planets in a disk shape, with some exceptions, okay? But not a lot of shifting, not a lot of angular shifting away from that ecliptic plane, as it's called, ecliptic plane. Now, the exceptions to that are non-planets, okay? Such as a dwarf planet that used to be considered a true planet, Pluto. We see that Pluto is shifted significantly. There's a large angular shift between the orbit of Pluto and the ecliptic plane. That's also true of the other known dwarf planets. There is one dwarf planet that is known in the asteroid belt itself, Ceres. It's the only asteroid that's big enough to be considered a dwarf planet, existing in the asteroid belt between the orbits of Mars and Jupiter. It's only slightly tilted, and that's due to it being so close into the solar system and affected by gravitational pulls from the Sun and Jupiter very, very significantly. But the other known dwarf planets are way out on the edges of the solar system in a region known as the Kuiper Belt, and those include Pluto, all right, again, used to be classified as a planet, now it's a dwarf planet, Haumea, Makemake, and Eris. And what all these dwarf planets have in common, besides being in composition like a very large comet, in other words, icy, and with some rocky pebbles within that ice, they have orbits that are significantly tilted to the plane that all the planets are in. Okay, and that's a big part of their orbital dynamics, is that they're not big enough to be part of that major planet category. Okay. So when we look at the terrestrial planets, we look at their surface and we see that many of them are pockmarked. All right, so terrestrial worlds like Mercury, the planet closest to the sun, is covered in these leftover impact craters from asteroids. Okay, and this right here, this image shows a black and white photo that's about 400 kilometers wide, and it's just covered in these impact craters. Now, the reason a planet has a surface like Mercury, or we could say the reason that Mercury has a surface like that shown in the image, is because Mercury is geologically dead. It was active at some point. It would have been a molten liquid planet like all the terrestrial planets very early in the history of the solar system, but then it cooled rapidly, and now it does not have an active core. There's no volcanism on Mercury. There's certainly no plate tectonics like that drive earthquakes here on Earth. Instead, Mercury is just dead in a geological sense. And so what we see are these leftover impact craters, left over from a period of heavy bombardment that occurred in the first 500 million years of the solar system. Okay, so the solar system is about 4 billion years old, and in the first 500 million years, which is half a billion years, there was a huge amount of leftover asteroids and comets. And so the planets, which were basically fully formed at that point, were being just impacted again and again with tons and tons of craters. So lots and lots of craters. And we'll talk about how in a few slides, how that can tell us something about the age of planets, and specifically the age of certain regions of planets. Now, in the case of Mercury, it's basically the whole planet is covered in these craters, just like very much like our own moon. Because the planet has been geologically dead for so long, there's been nothing to cover up these craters. There's also no atmosphere on Mercury or our moon, which have a lot in common despite their very different positions in the solar system. But the Mercury and the moon, having no atmospheres, have no way to, say, cover these craters with weathering effects. There can't be any wind, there's certainly no rain to cover them up, so they remain and have remained for billions of years, telling us about the very early history of the planet. Now, these craters would have occurred after the planet cooled, because I mentioned at some point the planets, all of them, Mercury included, and especially the terrestrial planets, were liquid in nature when they were being formed because they were so warm from all the leftover energy of their formation. That allowed the denser materials to sink down to the cores. So all the terrestrial planets have dense cores. In fact, the material of the terrestrial planets, like Earth and Mercury and Venus and Mars, the four terrestrial planets, is all fairly dense, but much lighter on the surface. Okay, and we'll talk about this when we talk about the planets in future chapters, because we'll be diving into each of the planets in more detail in future chapters. This is just an introduction in this chapter, because we'll talk about the solar system in more detail in chapters 8 and 9 and so on. But if we think of the planets as having a core, and then that is very dense, and then outside of that dense core we have lighter material. And that is true of the terrestrial planets, and it's also true of the Jovian planets shown here. The four Jovian planets: Jupiter, Saturn, Uranus, and Neptune. They also have dense cores. Now, their dense cores can be explained as an ongoing phenomenon of what's known as differentiation. Because differentiation says that denser material sinks to the bottom or sinks to the core of the planet due to the pull of gravity. Well, that happened for Earth when Earth was in a liquid state, very, very early on in the first few million years, before even heavy bombardment. And in those early few million years of the solar system, when Earth was in a primordial state, yes, those denser materials sunk to the core, and we have a dense core. Okay? But that is still going on because the gas planets are gas and then heavily pressurized gas into a liquid state, but they don't really have a solid except at the very core, where heavy material has sunk and then amalgamated into a dense core of these gas planets. And that actually is an interesting idea. The gas planets themselves are not entirely gas. They do all have rocky cores. Rocky cores, in the case of Jupiter, is bigger than the planet Earth itself. And that rocky core is this highly pressurized rock that's sunk down to the gas and liquid of the planet. All right, so let's look at some just general details. This is a table from your book that lists all of the 8 planets here. We have the 4 terrestrial planets and the 4 Jovian planets. 4 and 4, 8 planets total. Okay, we can look at their distances from the sun. There's a lot to be told about these units. If we look here, we have an AU. Well, an AU is a unit that's equivalent to about 300 million kilometers, and it's classified as 1 AU because it's Earth's average distance from the sun. So the nice thing about measuring distances from the sun, or average distances from the sun, because they're not perfectly circular orbits, but any of the planets, although some are quite nearly perfectly circular, but talking about those average distances from the sun as multiples or fractions of Earth's orbit is a good comparison to Earth. So we can see, for example, that Venus is about 72% as far from the sun as we are, and then Mercury is only 40% as far from the sun as us. So it's quite close. It's over twice as close to the sun as us, which is why Mercury is so bombarded by so much heavy radiation that is emitted from the sun. It has such hot days, and it can't sustain an atmosphere. It also has a small size, which makes it hard to gravitationally hold onto an atmosphere. But even if Mercury was the size of Venus, it still could not hold onto an atmosphere because of the strong solar winds that exist that close to the sun. And then we look at Mars. Well, Mars is about a half AU further, so it's significantly further out, so it's a colder region of the solar system. But notice the big jump here. When we go from the orbital distance of Mars to Jupiter, we go over twice as far. So then we can think of the terrestrial planets as all being rather crowded together close to the sun, and then a big gap until we get to the orbit of Jupiter. And we see that big gap persist because we will have to double the distance from the sun to get nearly double the distance to get to the orbital distance of Saturn. Okay, and then we double that again to get to the orbital distance of Uranus, and then we add half as much again to get to the orbital distance of Neptune. Neptune is 30 times further from the sun than Earth, right? Because it's 30 AU as compared to 1 AU for Earth. That is incredibly far out in the distant edges of the solar system. There's very little light energy that reaches a planet as far away as Neptune. The sun would just appear as a fairly bright star in the sky from the perspective of Neptune. It's not even the brightest object in the sky. It just gives you an idea about how far away Neptune is from the sun. Okay? So, putting that into perspective, we see that the Jovian planets are very far spread apart, And that has to do with their formation, the fact that they collected gases, and in doing so, they had to collect gases from a vast region of space. They sort of swept up the gas from each of them from vast regions of the early solar system, and then divided that leftover matter into bands that eventually condensed into the circular planets, the spherical planets that are the gas planets we see today. Okay, but that gravitational pulling in of gas is why they're so far sparsed apart. Also, an interesting thing about these planets is they all have very fast revolution periods. And by these planets, I mean the Jovian planets, which is very counterintuitive because they're massive in diameter. All right, so the Jovian planets are huge compared to the terrestrial planets. Excuse me for that. The terrestrial planets, for example, have a diameter in the case of Earth of about 13,000 kilometers. Well, Jupiter is 10 times the size, 10 times the diameter, much, much bigger. 10 times the diameter, that means it's about 100 times the volume, right? So about 100 Earths would fit inside of Jupiter. So very, very massive planet. But yet it's spinning 11 times faster, all right? Its revolution period, the time it takes to spin around its axis is so much faster in terms of its actual orbital speed. Okay. Oh, actually, let me fix this real fast. I said something slightly wrong here. So these here are the revolution periods. Excuse me. This actually refers to how many years it takes for the planet to go all the way around the sun. There's another bit of information that isn't included in this table, which is the actual period of revolution around its own axis. So if I was to consider that here, let's sort of split this column. We could then say this is the length of a day, all right? So Earth has a day that is 24 hours. If we consider the time it takes to spin all the way around for a planet like, for Jupiter, we actually have a pretty fast amount of time for it to spin around. Its day is not it's spinning very quickly. I don't have the number in front of me right now, but the length of the day for Jupiter is actually quite fast. I bring that up because despite its large size, or large sizes, all of the Jovian planets have short days. Okay, they don't spin slowly around their axes. They have very long years, as was noticed here in terms of the period. It takes 11 Earth years for Jupiter to make a full revolution around the sun. I was saying that incorrectly a moment ago, but this is referring to the time it takes in Earth years to go all the way around the sun. That has to do with the fact that due to weakened gravitational pull, the distant Jovian planets are moving slower relative to the sun, and they have much larger orbits to complete, as we saw back here, right? Their orbits are huge. If we look at, say, the orbit of Neptune, to go all the way around the sun, that's an incredibly large circumference. So it takes a lot of time for Neptune to complete that incredibly large orbit and moving slower along the way, which means that Neptune takes 165 nearly Earth years to complete one Neptune year. So that's pretty dramatic. But that's an interesting story in and of itself. But I do want to also point out that the day length for these very large planets that are moving very leisurely around the sun is actually quite short, because the planets are spinning very fast around their own axes. They have short days, shorter than 24 hours. I believe it's around 12 hours for Jupiter, and even shorter for Saturn. They have very short days, which is so counterintuitive considering they're on average maybe 10 times or 5 times larger than the diameter of a terrestrial planet like Earth or Venus. And that's just due to conservation of angular momentum. These larger gas planets, they have amassed so much gas in their formation that all that gas is spinning as it formed, and that spin is left over. In the case of the terrestrial planets also spin, but their spin is much less predictable. Their spin is more determined by certain large collisions once they had come together as rocky planets. And so we see that some planets have very, very slow spin. So Mercury has a day that is about 2/3 as long as its year, and Venus has a day that is as long as its year. So Venus is barely spinning around its own axis. And so the rocky planets, their spin is much more unreliable, and it seems to be determined by particularly large collisions with these rocky planets after they're formed. But the fast spin that is true of all the Jovian planets is a conservation of angular momentum story, despite their large size, all right? And their high mass. Because we can see here, if we consider the mass in multiples of 10 to the 23 kilograms, an unbelievably large size, we can see that Earth has a mass of 59.8 times 10 to the 23 kilograms, and Jupiter here has 18,000, nearly 19,000, that number of kilograms, right? So in comparison, right, we can see that the mass of Jupiter is incredibly large. In fact, even compared to Saturn, which is not that much smaller, Jupiter is much more massive. Notice these two numbers here. Notice the difference between the mass of Jupiter and the mass of Saturn. Their radii, not that different, right? There's an extra 20,000 kilometers in the diameter, not radii, but the diameter of Jupiter. But look, it's over 3 times the mass for Jupiter. It's definitely not over 3 times the size. Why is that? Well, that's because Jupiter is denser. What's happened is gas collected in Jupiter in the early stages of the solar system. Jupiter got denser and denser because more and more gas collected. And so its core got denser. And if Saturn had collected more gas, Saturn would not have grown much in size either. It would got denser first. So there's a process in the formation of gas planets where they get large up to a certain size, about Saturn size, but then as they collect more mass, as Jupiter did, they don't grow much more, they just get denser for a while. And eventually they will grow a bit in size, and if Jupiter was about 5 times its current mass, then it would actually be so dense it would become a star. But it's a long way from there. It'd have to be 5 times its size to become a star. Okay, so we never had a chance of having a second star in our particular solar system, but there are plenty of other solar systems where there are 2 or more stars. And then finally, we can look at those densities as I was hinting at. We can see that the terrestrial planets all have high density. All right, they all have density that's significantly higher than water because the density of water is 1 gram per cubic centimeter. So it's 1 gram per cubic centimeter. All right, so we can see all the terrestrial planets are much denser than water because they're rock, and rock is, they're primarily rock, right? And so rock is much denser than water. You think of that, put a rock in a body of water, it sinks. And so indeed, the terrestrial planets, the rocky planets, are dense. But look at the Jovian planets. The Jovian planets are all very low density. And that's because they have gas, huge amounts of gas on a very thick atmosphere. That there's no surface to the Jovian planets, but if you were to dive into the atmosphere of the Jovian planets, the gas just gets higher and higher pressurized as you go deeper and deeper. Eventually it becomes so pressurized it phase changes into a liquid, and then all the Jovian planets have this pressurized, huge liquid ocean that's underneath their cloud layer. And and there's like kind of a gradual change into that high pressure state. But still not that dense. And certainly not denser, not that much denser than water. In fact, Jupiter and Uranus have about the same density. Neptune is a bit denser. The only planet that has a particularly low density is Saturn. Because Saturn just has a greater amount of hydrogen than the others, and it's just the lowest density. In fact, it's the only planet in the solar system that's less dense than water. Saturn, if it could, is the only planet that would float. Now, an interesting thing about these low densities is it's really indicative of the fact that all of these planets, Jupiter, Saturn, Uranus, Neptune, well, that one thing they all have in common is they're primarily hydrogen. Primarily hydrogen. All right? So yes, there are other elements, the next most common being helium, but hydrogen is by far the most common element, which is the most common element in the universe, the most common element in the sun, so we shouldn't be surprised to see it in high concentration in these gas giants. Now, it's not true with the terrestrial planets. The terrestrial planets, because they're so close to the sun, all that hydrogen just got pushed away, evaporated, and eventually made its way out to the outer solar system. And so there's not that much hydrogen left in the inner planets, like Earth and Venus and so on. There's some, but not that much, okay? So here is something that's not a planet, Pluto. Recently, there was a New Horizons spacecraft that flew by Pluto, launched many decades ago because it's such a long journey. And we found that Pluto is so fascinating because Pluto, like other of these dwarf planets, as far as we know, in the outer solar system, and similar composition icy moons, is actually geologically active. It has icy volcanoes and big like outpourings of gas and so on. So you might think that it should be geologically dead, like say Mercury, but it's not. It actually has geological activity, and that's due to the much lower melting point of ice than rock. So that ice is constantly able to melt and move around within the core of the planet, or a dwarf planet in this case. And we see that with the icy moons of the Jovian planets, which we'll talk about more when we talk about the moons of Jupiter and Saturn, which are very fascinating. Here's a picture of Saturn and its rings. Interesting thing about the rings, Saturn has dramatic rings by far, We think that that's just a transient effect. The rings of Saturn have not lasted for billions of years at all. They probably just last for a few 100,000 or millions of years, and then they eventually will get darker in time as they get exposed to radiation and other elements and sort of some oxidation processes, and they won't be so brilliant and reflective in a few million years, and then eventually they might actually condense and kind of get, become very, very dark and hard to see. And then, so it's the particular bright rings that Saturn has is probably due to a moon collision that happened in the recent millions of years. Now, what's interesting about rings in general, as I was starting to say, is that all the Jovian planets have rings. So Jupiter, Neptune, Uranus, they all have rings. They're just darker rings. Saturn is the exception. Here's a picture of an asteroid, the asteroid Eros, that had a flyby taken by a mission here, right? There was a mission that landed on Eros. And it's the thing about asteroids is asteroids are rocky leftovers. Okay, so they have a composition similar to the terrestrial planets, sometimes much denser than the terrestrial planets, because sometimes they are almost entirely metallic. There are also asteroids that are more carbon-based, and there are asteroids that are more rock-based, like silicon-based. But regardless, they're all dense, some sort of rock or metal, and and you find them in the inner solar system. On the other hand, comets are found in the outer solar system. Comets are generally bigger than asteroids because they have some frozen hydrogen-based gases. So comets cannot exist on the inner solar system. Now, sometimes they'll pass through the inner solar system where they start to evaporate their outer layers, creating the dramatic tail that comets are so well known for. But most comets spend their lifetime out in the distant edges of the solar system, even further than dwarf planets like Makemake and Pluto. And way out there in the edges of the solar system, they're just frozen clumps of hydrogen-based gas. All right, so frozen H2O, yes, actual frozen water, frozen methane, frozen ammonia, and they also have heavier elements in them, but because those hydrogen-based elements that are evaporate on the inner solar system are able to condense on the comets, they're primarily made out of those lighter elements, what would be a gas on the inner solar system. So really the only difference between an asteroid and a comet is that comets are in the outer solar system, so they can have hydrogen-based ices. Asteroids in the inner solar system where those ices would evaporate, okay? And so in a sense, a comet could become an asteroid if it moved to the inner solar system, but it would just become many small pieces of asteroids, just the leftover heavy elements that wouldn't melt and evaporate, okay? Here are some famous science explainers, communicators of science. Carl Sagan is well known for his series called The Cosmos that was then redone by someone that was kind of his protege, Neil deGrasse Tyson. So Neil deGrasse Tyson, Carl Sagan was his mentor. He then made a show with the same name called Cosmos. These shows are great for introducing astronomy to the general public and such well-known faces for communicating science, in particular astronomy. All right, here's a actual flyby picture taken by the Cassini spacecraft of Jupiter. We can see Jupiter's upper cloud layers. The different colors refer to different depths. So we kind of have some transparency between the different depths of the cloud layers. We'll be talking about Jupiter more in future chapters. But this is a Jovian planet. This is a gaseous planet, right? And the biggest planet by far in the solar system, as we saw on the table. Here is one of the moons of Jupiter, Ganymede. Ganymede has a composition that is rockier than Pluto, but not terribly unlike Pluto, right? Definitely Ganymede's a bit more rocky. There's another moon called Callisto that's really has a composition very similar to Pluto, but it's an ice and rock-based moon, okay? And covered in pot marks, right? We can see where these represent impacts from craters. These would they have a particular kind of look to them because they've sort of thrown up ice. That's why they look like these kind of like white spots. All right. Here is this idea that collisions are still happening today. There was a comet that collided with Jupiter, leaving this trail of damage taken by this telescope. Okay. And we can actually see here, taken by the Hubble telescope, we can see the leftovers of the same collision by the comet Shoemaker-Levy 9, where you can see these huge dust clouds that were stirred up in the atmosphere of Pluto that took some time to actually settle down. So it was an incredibly dramatic collision. These dust clouds are the size of Earth. If a collision like this happened on Earth, it would be an extinction level event, and it happened back in 1994. Now, the thing is that Jupiter is actually helpful for protecting Earth because of its large gravitational pull. It's more common and more likely, probabilistically, for comets like this to crash into Jupiter than make their way all the way to the inner solar system and crash into a planet like Earth. So Jupiter acts as a gravitational pull, thus a buffer protecting Earth in a sense. Okay, and so certainly, we'd rather this comet crash into Jupiter than us. All right. Here's our cratered moon. I mentioned that the totally covered surface of the moon in craters is kind of similar to the surface of Mercury, covered in craters. And I also mentioned that we can use these craters to estimate age. So this is actually the far side of the moon that we're showing here. And the far side of the moon has surfaces that are older than the near side of the moon, because the near side of the moon has these large lava flows that have covered up the craters. And since that era of bombardment ended at some point, there's not that many craters on top of the lava flow. That allows us to date that lava flow. We can say, oh, the lava flow happened at a certain point in the history of the solar system. And it's very important for allowing the amount of craters to have some estimate of dating surfaces on the terrestrial planets. Not at all helpful for dating surfaces on the Jovian planets because they don't have a surface, right? A collision just sinks down into the atmosphere. But on the terrestrial planets, certainly we can date the surface based on the number of craters. That's also true of rocky moons. So moons like this one, of course, our moon, but also moons of the Jovian planets, like the moons of Jupiter and Saturn, which I mentioned. Well, their surfaces can also be dated by the amount of craters. In other words, there's a proportionality between the amount of craters on a stretch of the surface and the age of that stretch of surface, that area of surface. There is at least one example here. We can see this large area here, which is darker in color, would be a newer region because it was covered in lava at some point. And by the way, the reason there's more lava flows on the side of the moon that is constantly facing Earth is due to tidal frictions. The same forces that allow us to have tides also have heated up the sides of the moon in the past that's close, that faces us, thus allowing lava to flow more freely. However, those lava flows finished about 2 billion years ago, and there's no more active lava on the moon. Now, another way we can date things in the solar system, which is important, to have two separate methods of dating things, is to use radioactive decay. This allows for radiometric dating because there are certain elements that exist, common elements, that decay at a steady rate. In other words, we can have a sample that is entirely some type of element, like uranium. And after a certain number of years, that uranium will have decayed. Some of those atoms will have decayed, becoming a different atom on the periodic table, a different element. And if we know the half-life of how many of those individual atoms have decayed, then we can actually measure the sample, find out that there's half as much uranium as we started with, so half the uranium we started with, and now half of something else, the byproduct of the radioactive decay. And since there's half and half, we know that one half-life of time has passed. So if the half-life, for example, is 1 billion years, which is a long half-life certainly, but a half-life it is, kind of relevant for certain isotopes of uranium, then we can say if we could find a sample that has half of pure uranium, then we know that formed in a certain process where the initial sample would have been pure uranium, then we know that rock is 1 billion years old. Okay, or however long the half-life happens to be. In this case, BLY for 1 billion years. Okay, now different half-lives, some half-lives are only a few thousand years. Those are more helpful for biology, not really used in dating the solar system. But these half-lives of certain elements that are hundreds or billions of years are helpful for dating the solar system, especially dating asteroids, because asteroids were formed in a certain molten sense, and then they've just been decaying ever since, and they haven't been interfered with. After that, there's been no geological properties to interfere with those asteroids, and so they've remained in a pure sense, just gradually decaying, which allows us to date those asteroids and thus date the solar system, because we find the oldest asteroids are about 4.5 billion years old. Based on radiometric dating, that gives us a good number of how old the solar system is. That's once really our sun started undergoing fusion. That's once the leftovers from that didn't gravitationally pull into the sun started forming the planets. That was about 4.5 billion years ago, and since then the planets formed and everything else has happened. Okay. And then we can compare that number to, as we talked about, the amount of bombardment on the surface of a planet to make further dating estimates, such as the one that I mentioned early on in these slides, that heavy bombardment lasted about 500 million years. That's a combination of dating based on radiometric dating and comparing bombardment between worlds, planets, and terrestrial moons. Okay? So that's the idea of radiometric dating. There's a particular formula used for this process that you can look at in the book as well. Okay? Now, one thing about the solar system is we think it, as I said, it formed as the sun formed. It formed from what's called a solar nebula. That's basically the cloud of leftover material around the hot star that was starting to undergo fusion. And we see that process throughout the galaxy. As we look at other stars that are forming, we see them having that planetary nebula. We see those planetary nurseries. Now, on a larger scale, we see huge nebula that are nurseries for stars. But when we look at individual stars, now with our better telescopes that we've had in the last decade or so, we can actually see the nurseries for planets themselves. And we have discovered hundreds, now actually thousands of planets. Not just them forming in the case of these disks forming around stars that will eventually become planets, but we also have seen tons of evidence of individual planets fully formed. And we found lots of interesting aspects about these planets around other stars. For example, the way that there's some solar systems seem to differ from ours. And it helps us understand the basic principles that drive solar system formation. It helps us understand our own solar system better by looking at other solar systems. So it's really been a breakthrough in science that we can look at other solar systems, look at how they form, and look what they look like once they're fully formed. Well, that concludes our lecture on Introduction to the Solar System. You'll have plenty more to learn about the solar system in the chapters to come. Thank you so much for watching this lecture, and I hope it's been interesting and informative.